All right. So, just to reiterate, in case you're just joining us now, this is contracting. No, we don't want that. So, how do we get it back to where it was? Because we should be able to say like, oh, I'm running this sim, and I expect that when I run a high-res sim, it will look the same, just with more details. So, that's kind of the idea of upresing something. So there are several ways. The first and maybe easiest way, only in the sense that I wish it wasn't doing that. The easiest way is you can increase the number of substeps. You may have to go all the way up to four sub steps. So simply putting this, or if you want to be really sure, you can put the minimum as four also. If you don't put the minimum as four, it will try to determine how many it needs based on how fast the particles are moving. It was almost certainly just after the first couple of frames, just choose 4 and 4 anyway, or just choose 4, I mean. But some people like to do 4 and 4 so that it doesn't vary. But in any case, so you could do that and run it, and it will probably work. The problem with that is it will take twice as long to run. I would also say that it might feel a little different also. Right now, with this, we have, we have a certain feel. I mean, the feel at least is fairly similar to our lower res one here. But if you give it more substeps, it gives an opportunity to do more movements between frames, which is good in general, but it might feel different. It might be better, but it will be different maybe than what you anticipated. You might get more splashing, for example. That's a kind of a common thing from more substeps. The water can break apart a little bit more. Yeah, essentially it gets more sub movements, which can lead to more detailed movements, which can lead to essentially more spraying movements. So again, if you got used to this feel, you can already see at the higher res that there's more little breakup and stuff. So you might get a little even more than that if you increase substeps. So that's one way of doing it. Another way of doing it is what we're going to talk about now, which is a cheat way, so that it doesn't feel as different, and it also runs not as, at 4 substeps. So what that is called the gas equalize node. Gas equalize is a solver, a microsolver, I should say. A gas equalize volume. And what you can do is, on your liquid sim, plug it into the volume velocity, which is the third input. It won't work the same on other ones, but put in this one. And the method by default is divergence flip. So before I even explain what that is, you must remember under initial data on the flip object to turn on add divergence field, or this will not work. You might think it's working, but it won't actually be doing anything. And you'll know when it looks the same. So, what is the gas equalized volume? Gas equalized volume essentially is saying that, this has a surface sine distance function, which, as you know, well, by now, defines the volume of the kind of the extents of the liquid. Now, given that and how many voxels there are, one could calculate the total volume of liquid in the simulation just by counting all the voxels that are inside of it and then the fractional ones along the surface. Now, we don't have to manually do that, of course. Houdini is perfectly capable of doing that internally. What gas equalized volume can do for you is you can give it a goal volume and say, try to be this volume. So if we already know what the volume is that we want, which we know from the, let's say, the previous sim that we did, this one, we can say, like, well, on this frame, what was the volume? And that will literally be a number that we can literally plug into here. So this is really annoying. I guess turn this off. I don't know. Anyway, let's just ignore that for now. That's better. So let's find out what that volume was. I can go to liquid cache. Let's go to the last frame. I don't even need it to load this. Let's load the previous Sims one. I'm just pressing escape to not load these high-res meshes. Okay, so here's the previous sim, which again is what we're trying to emulate. That's the whole idea here. So I'm using the same unpack from before when we were trying to figure out the speed. So it's polygons or polysoups. In fact, this does need to be polygons in order for this to work. So put a convert down. And now we have, there's a couple way of doing these measurements. We could count up the voxels like I said earlier. The more standard way of doing this is with the measure stop. And we might as well do it this way anyway because this is the literal visual representation that we're trying to match. So change measure to volume, and yes, you can calculate the volume of a mesh. Every triangle, each square here is chopped into triangles, and each triangle does makes a tetrahedron to a certain point in space, and then you can get the volume of each tetrahedron individually. So you essentially are getting the volume of each triangle. So that's kind of fun. So if we were to look at that, you'll see we have a volume attribute now on the primitives. They're all pretty small. And so what we want the total volume though, so we want to add them all up. So promote attribute, primitive to detail, the volume, and we want to add them. So sum them. So what does that get us? On the detail, apparently it's 9.91048. You might as well just write that down or something. We could lock this or make a cache of this. I mean, I don't think we need to go that procedural. I'm just going to say 9.91048. So we just have it lying around there. So that's pretty much it. We can go back now to our regular settings. We need to make sure that this is going to be set to version 2 now, which of course doesn't exist yet. Yeah, we're going to save yet another high-res version. I know you might not be too thrilled about that. You could, if you wanted to, just overwrite. I think I told you not to do a version 1 anyway, so this will probably be your version 1, if anything. Or you can skip to version 2 to follow along with me. Anyway, so we have this number, and now let's go use it on the Liquid Sim. We need to go to there we go, the gas equalized volume. So say scale goal volume to be 0, and then add goal volume to be that number. We're not giving it a goal volume. That's the thing. So if we didn't do that, it gets screwed up. So just do that and that. There's a bunch of settings on here as to how fast it will try to get to this volume. So what's going to happen is, I should really just say what it does. Divergence is a field, much like in Pyro, which is simply just saying expand things or contract things. What we're going to do is every frame we're going to sum up the total area of the surface field, which is already part of Flip, and if it's lower than this, it's going to add value to the entire divergence field. And the divergence field is used by the Pyro solver to say, should I expand or contract? So it's going to expand everywhere. It's not ideal. We would rather the simulation just do this. It's not great that it's going to expand every water droplet, every tendril. The hope is that it will do this every substep, of which we have 2, and every frame, of which there are 24 in a second. So as long as we can incrementally do it and start to do it, once it starts to shrink, like as it starts to shrink here, we can just add little bits just to keep it at the right amount. So as long as we only have to do very small adjustments every frame and subframe, we should avoid getting to this. Like if we had to start from here to get back to this, it would look very strange. Or rather, to get back to this, it would look super weird. So the idea here is that we'll just use little tweaks every frame to keep it where it's supposed to be. How fast it tweaks it, like how much expansion should we do? Well, the max change limits it to 3 voxels, but we don't even really ever want to do 3 voxels. Hopefully it doesn't come to that. The integral coefficient is how fast it moves towards it. Now I want it to move pretty fast. I just wanted to do it, per frame before it, gets a chance to get too small. So make it bigger. You might even make it bigger than this. 10 is pretty big and should be good. If it's not, we'll run it again. But so that's pretty much it. Add divergence field. Remember, that's on. This is divergence here. The last thing we want to do is in the proxy sim, which we'll run again just for completeness, this should be off. So go to auto takes and turn that off. We already know that it works fine in the proxy sim. We know the proxy sim is not collapsing. I don't want to confuse it by giving it some different goal volume than it was already going to do. I mean, it would work, but we're going to get a different result again. It might be bigger, and then our whole thing is going to get... just don't even bother. We already know the proxy sim part works, so just don't do it on the proxy sim. So that's pretty much it, actually. That should work. You can visualize it by turning on the guides. Sorry. On here, you can turn on divergence. I'm not going to do that. All it does is it makes a big plane that shows you the divergence field, and the divergence field doesn't look like anything. It's just going to be all one value. In our case, it doesn't have to be, but in our case it will be. And it will have a color that will basically say if it's adding or subtracting right now. So we'll know if it works or not just by the result of our sim, but the visualization is not going to be useful for us right now. But it is good to see if you get no result, then see if you get a divergence thing. The problem is that the sim takes forever to run, so I don't plan on doing a flipbook in here first to see it in the viewport, which is what you'd have to do to see this visualization. Okay, the last thing I'll say, and I don't usually like to do this, but I would say the help card itself has a good example. This never works for me anymore. Well, if it works for you, look up the gas equalized volume card. There's some examples on the bottom if you do want to see the visualizer in action. It's a pretty good example of how it works.